So, ladies and gentlemen, what we're going to talk about today is a particular type of reaction called a precipitation reaction. Okay? Now, let's just make sure we understand what in chemistry, not in weather, what does the word precipitate mean? An insoluble solid, she says, that forms, and I'm gonna change what you said at the end just a little bit, that forms when you combine two aqueous things. Okay, but the point is, a precipitate is a solid product. Okay, and this is what it would look like. You combine two aqueous solutions, and you would see this. Okay, now that may not look like a solid to you, but over time you would see that it settles to the bottom. If we poured the contents of this beaker through a filter with some filter paper, you would see that all of the liquid would run through and the solid would stay on the filter paper. Okay? And it's hard to see, I know, it's written kind of small, okay? But this is the reaction that's going on. Okay, we've got two aqueous solutions. Now let's review. What does the word aqueous mean? Yeah, something's dissolved in water. Water is your solvent. Okay? Now, dissolved. We talked about this last class. Okay? What does it mean when an ionic compound dissolves? Like, what actually happens? Yeah?
It ionizes, breaks into its two constituent atoms.
You got it. Thank you for using the word ionize, okay? It ionizes. It breaks down into its two ions, and that's exactly what happens, okay? And we get one aqueous product, but one of our products is solid, okay? And as she said, why is it solid? Because it's insoluble. What does insoluble mean? Yeah, cannot dissolve, will not dissolve. Okay? And if it won't dissolve, that means it stays in solid form. Okay? So that's what a precipitation reaction looks like. Okay? This is the same reaction that was just written on the previous slide. So here's the deal. All right, this was the reaction that's taking place. And as he said, when an ionic compound dissolves, what happens? It breaks down into its two ions. This one is also aqueous, will dissolve, so it splits into its two ions. Right? Same with this one. This one, our precipitate, does not dissolve, so we keep it as is. It does not ionize. And I'm sorry I couldn't write this all in one line. Okay? But guys, tell me this. Think about in your math classes. If you have a fraction and something in the numerator and denominator are exactly the same, what can you do? Cancel it out. Okay? Well, guys, chemical equations are very similar. If you have something that is identical on either side of the arrow, you may cancel it out. So look at this equation. Do you see anything I can get rid of? Okay, potassium, gone. Nitrate. Can I get rid of anything else? Nope. Okay. And this is what I have left with. Okay. Now, it wasn't balanced up here, and that's okay. When I got down here, then I balanced it. Okay. This, ladies and gentlemen, is the real reaction that's taking place in the beaker. Right? Now let's say something about these ions that I crossed out. Okay? Please understand, it is not that those ions are not there. They are there. Okay? The ones that I crossed out have a name. They are called spectator ions. Okay, spectator ions. And think about that word. Okay, if you go to a soccer match and you are a spectator, are you playing in the game? No. But are you at the game? Yeah, you're there, but you're not playing in the game. These ions are present. They're just not part of the real reaction. They are just floating around in the solution, not doing anything. Okay, but they are there. Right? So, this type of reaction is called a molecular equation. Okay? Okay, so this is called a molecular equation. This is how you've been writing reactions, all through Chem 1. When you break it down into its individual ions, and how do you do that? Based upon whether it's soluble or not. That's called a complete ionic equation. When you then cancel out your spectator ions, you get down to something called a net ionic equation. All right? Now here's the million-dollar question. How are you supposed to know what's soluble and what isn't? Am I going to tell you? What do you think? Nope, I'm not. So how are you supposed to know? There are a set of rules called the solubility rules. Okay, now let me say first and foremost, because I bet you're thinking this. Do we have to memorize this? No, you don't. Now, you do have to memorize some, but not all. Make a note, though. I expect you to have memorized, and really the AP exam does too, the first 2 rules. Write it down. Those need to be committed to memory. So what are those rules? Okay? What these rules are telling us is what kind of compounds are soluble or not. So rule number 1, any compound that contains nitrate or acetate, automatically soluble, no matter what it's joined to. Any compound that contains an alkali metal or ammonium, soluble, no matter what it's joined to. Where are your alkali metals? Which group? Group 1. Okay, good. So those need to be committed to memory. What else is there, though? What do you think I mean by this word halide or halide? What does that sound like off the periodic table? Halogen, okay? This means a salt, any salt that contains a halogen. However, there are some exceptions. If your halogen, doesn't matter what it is joined to silver, lead, or mercury, that will be insoluble. Okay? So, pick a halogen, guys. Any halogen you want. Pick one. Fluorine. Okay? So, magnesium fluoride, soluble. Silver or lead or mercury fluoride, insoluble. Okay? Most salts that contain sulfate will be soluble. However, there are some exceptions. This one, you actually already know. We talked about this one last class. Go back and look at your notes. What's another way to say a compound that contains hydroxide? A base. Okay? So what this is saying is most bases are insoluble. However, look at what's in the parentheses. This should look familiar to you. What is in this parentheses? How did we name this group? last class?
Strong base.
Your strong bases. All right, and let's review that. What does it mean to be a strong base or a strong acid or a strong electrolyte? What did that mean? Yeah, they completely ionize. And guys, we're making connections here. If it completely ionizes, doesn't that mean that it is soluble? Say yes. Yes. Okay. So this you actually already know. Okay. Most of your sulfide, carbonate, chromate, phosphates, most of those are going to be insoluble. And you actually know this one too, because we talked about this last class. Do you remember the little mnemonic device I gave you to remember the strong acids? Imagine a perfectly clear, breezy summer night. Okay, so let me give you an example. I'll put it up on the board. Let's say you had lithium carbonate. Look at your rules. You guys tell me, is lithium carbonate soluble or insoluble? Okay, I hear both. Give me a reason, defend your argument for it being soluble. Yes, sir.
Because it contains lithium, which is an alkali metal.
Okay.
And that pulls preceding metals.
Okay, so he says it's got an alkali metal in it, which says soluble. Somebody defend the other argument. Why do you think it's insoluble? Okay. This one right here? Yeah. Most carbonate salts, insoluble. So we have conflicting information here. All right? And you hinted at this a little bit. How do we know? Because lower number rules. What I mean by that is one's up here, 1, 2, 3. Those rules supersede lower rules, or they're more important than lower rules. So what's the ruling here? What do we think? It's soluble, okay? So what are we going to do with this? Well, on your next test, what I am going to give you are questions that look just like this. I will give you reactants in words. I'm going to, number one, expect you to predict products. And number two, I'm going to expect you to get down to the net ionic equation. We're going to work number one together. Okay. Iron 3 sulfate and potassium sulfide. So the first thing I'm going to do is write out my molecular equation, just like you did in Chem 1. Okay. What is the formula for iron 3 sulfate? Tell me. Fe what? All right, Fe2. All right. Potassium sulfide. What do you got? K what? K2S. Okay, now let me say something about predicting products, because on our last test it was very clear that many people are uncomfortable or don't know how to predict products. And guys, that is something you just have to figure out. If you are uncomfortable predicting products, then you need to come and see me at some point. Or even talk to your Chem 1 teacher, because the AP exam and I are going to expect that you can do that, right? But let's talk it out, okay? This is a double replacement reaction. One thing that I find if you're uncomfortable predicting products is switch the words there. Tell me in words, what is one of my products? Yes, sir. Okay, potassium sulfate. What's the formula for potassium sulfate? You got it. Okay, everybody, what's the other product in words? Iron 3 sulfide. Give me the formula. You got it. Okay. Okay, our next step is to write out what's called the complete ionic. How do you do that? You look at your solubility rules. Okay. So we're going to go compound by compound. Here's your first one. Look at your rules. Tell me what you think. Soluble or insoluble? Okay, she says soluble. Defend your argument. Yeah, most sulfate salts are soluble. Is iron sulfate one of the exceptions? No, it isn't. Okay, now guys, watch carefully what I'm going to write on the next line here. I am going to completely ignore those subscripts. I'm going to write just the bare ions. So iron with a +3 charge. Sulfate has a -2 charge. I'm completely ignoring those subscripts. All I care about is what are the ions. Okay, next. What do you think? Soluble, insoluble, what do you think? Okay, you say soluble, defend your argument. Okay, it's got an alkali metal in it. But lower down it says sulfide salts are insoluble. So what? Yeah, the ones higher up in the list are more important, so this is soluble. Again, guys, watch what I write here. I'm ignoring that subscript. Potassium has a +1 charge. Sulfide has a -2 charge. Okay? This guy. Soluble, insoluble. What do you think? Soluble. For 2 reasons. It's got an alkali metal and it's sulfate. Both of those things are typically soluble. Okay, last one. This one. Insoluble. Why? Yeah, it says most sulfide salts are insoluble. Is there anything special about iron that like bails it out from that situation? No. So that one is insoluble, which means we keep it together. It does not split up. What can I cancel out? Okay, potassium, gone. And sulfate. What are those ions called that I just crossed out? Spectator, absolutely. Very good. Let's write what's left. There's my net ionic equation. Is it balanced? No, but it's easy to balance. Final answer. Okay. So that is the process. I'm going to have you do 2 and 3 on your own. Okay. Give it a try. Okay, ladies and gentlemen, I want to talk through number 3 because most people didn't have an issue with number 2. Okay, but number 3 is a little different. It's different because it's a single replacement reaction as opposed to a double. Okay. First of all, chlorine, ladies and gentlemen, metal or non-metal? Non-metal. In a single replacement reaction, the thing that is by itself switches with something that is the same kind, metal or non-metal. Chlorine and iodine are what are going to switch. How did I know this? Because how do you write iodine by itself? I2. Going down to the next line, and I said this to a couple of you, the solubility rules apply to compounds only. They do not apply to pure elements. So if you come across a pure element, don't change it. Keep it exactly the same, okay? In this particular line, the only thing I could cancel out was barium because Cl2 and Cl minus are not the same thing. They're not identical. This is a gas. This is an ion. So all I can do is cancel out the barium. This is what I'm left with, and then I balance it. All right, let me say one other thing. All right, a couple of people asked or got into a situation by mistake of, what if everything cancels out? Okay, such a reaction does, reactions like that definitely exist where all of the compounds are soluble. And if you cancel everything out, do you know what your answer would be down here in this box? No reaction. Okay? But let me be clear about something, and I'm going to shout a little bit here. Okay? On the AP exam or on my tests, I will never, 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 ever, ever, never, 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 ever give you a situation where the answer is no reaction. Ever. Because what's the point, okay? In chemistry, we're looking at reactions, okay? If it's no reaction, well, then I can't do anything with that, all right? So, did everybody hear me say that? Do I need to? Ever. Okay? Okay. Guys, we're going to put some math to this. And actually, I apologize. I should have taken this out. Just scratch out this statement. Get rid of it. You don't need it. Get rid of it. Pretend it's not even there. Okay? I'm going to set number 1 up for you. I'm always trying to model how do you break these word problems down into manageable pieces. Okay, so it says, what volume of 0.204 molar hydrochloric acid? Stop right there. I'm going to circle the word volume because that is my unknown. Okay, that's what I'm trying to solve for. We are given the molarity. If you have the molarity and you need the volume, what's the missing piece here? Think about how you calculate molarities. Moles, okay? In this case, moles of HCl, okay? The point is, the reason I wrote that down, if I can find this, which there must be a way to get it, if I have moles and I have molarity, I can solve this problem. So think about, how do you get here? Well, let's keep reading. So what volume of HCl is needed to precipitate? This is a precipitate reaction. All of the silver ions from a certain amount of silver nitrate. Okay, the language is a little hard to decipher, but ladies and gentlemen, this is one of your reactants. This is your other reactant. Okay? One other thing I want to point out, and you're going to see this combination over and over and over and over again. A volume and a molarity. You're going to see that combination given to you 1,000 times over. What can you get? What can you solve for immediately with a molarity and a volume? Moles. Okay? Be careful with your units. Molarity is moles divided by what unit? Liters, not milliliters. Okay? I'm going to let you guys work through this. What do you think is the very first thing you should do before you even start calculating? Write out a balanced equation. It doesn't have to be a net ionic, just a molecular equation. Okay, there's number 1. All right, let me introduce you to number 2. Okay. What mass of solid? I don't tell you what the solid is. You will have to figure that out. But you can. Here's one reactant, here's the other. You have your solubility rules in front of you so that you will know which product I'm talking about. Here's that combination again of volume and a molarity. We're going to see this 1,000 times over, as I said. And let me just set the scene before I let you go on your own. What kind of a problem are we dealing with when you are given amounts of not one reactant, but both of them? What's the situation? Limiting reactant. Okay? So, may I suggest that if you're not sure how to do a limiting reactant problem, you get that worked out ASAP, because you're going to see them all over the place. Okay, try this one. What's the first thing you should do? Write out a balanced equation. So there's number 2 in all its glory. How did I know which answer was the answer? The smaller one. Okay, and in a limiting reactant problem, and a lot of you miss this, you have to do 2 calculations.